I have a single slide, but are you guys prepared to put that up? Yeah, if you could. I'm just going to get started in the interest of time. So, how many people here are aware of quantum computers? Like you've read an article about it, something like that? Good. How many people are aware that a quantum computer allows you to compute things that we are probably never going to be able to compute otherwise? Fewer. And how many people are aware that in March, we kind of crossed that Rubicon where we're now able to do computations where, the Oak Ridge National Labs supercomputer was not able to compete with it? 1, 2. So that was in March. And we're rapidly approaching this apex where it's going to be useful for quantum computers to help you out in probably the next 2 to 3 years. And we're seeing advances. Right now, the main advantage is with the D-Wave computer. It uses something called an annealing algorithm. Let me give you a mental model that makes it useful to you as to when a quantum computer is going to help you and why. How many people think they have an understanding of how a quantum computer actually works? I know that's like already half the audience is gone. So nobody. Fantastic. How many people in school remember how they described like the I imaginary number to you? Okay, good. Talking to scientists, right? You're on the 0 to infinity axis, and suddenly I comes into play, and you've left the axis and you're in 2 dimensions. It's the same general principle with a qubit, right? So it's representing a 0 and 1, but it has essentially an entire vector map around it, a 3-dimensional map, and you're doing operations and you're moving yourself around in this space, and eventually you want to read that out, and that's what they mean when they say collapsing the state. So it goes to 0 or 1. In theory, you could have potentially more states than that, but let's just make it simple. So that's how quantum computers work. There's advantages and disadvantages to that. So the advantage is when you're doing classical computing, the analogy is, think about it like you're doing some sort of graph algorithm where you have to go a little bit along the x-axis, then a little bit along the y-axis, figure out where you are, and then maybe move back a little bit, move up. And that's useful. You can actually do computation that way. But with a quantum computer, you're just kind of like going directly to it. You're describing your mx plus y or mx plus b, however you learned how it worked, and you're going directly to the solution that you're finding. So you're constantly moving closer and closer to that result. The downside is you only get the answer when you read it. So the mental model you should have is it's closer, a qubit is like closer to a transistor. So we have 256-bit, 64-bit computers right now, AMD 64. I'm sure you've seen that in your research on the screen on the terminal. That's not what we're talking about when we're talking about qubits. You really want, hundreds of thousands, millions, billions eventually. And that's the first part of the mental model. The second part of the mental model is that this is never going to replace a traditional computer. And the reason why is we're going to have to build our problem space. We are going to run operations against it, and we're not going to know anything about the current state of the system until we go to read it out. So that's the mental map you need on quantum computers. But they enable you, instead of going, and doing this searching algorithm to find the answers to your problems, to go more directly to them. That's extremely powerful. So with that said, quantum computers, they're always going to be like a coprocessor, right? It's another type of GPU. And it's not great. It's not necessarily great at parallelization. GPU is like the ultimate parallelization processor. So the problems that you want are things that are going to be hard to parallelize, right? But they're trying to find relationships where you have to do a lot of interconnected types of relationship searching to actually do the computation that you need. So that's the general idea of what we're talking about. So right now they're $20 million, $40 million to buy one and build one. So the pitch to you guys from what we're doing is we're trying to get you access to these things on the cheap, right? So you're, the compute consumers, hopefully, and I hope a few of you are the algorithm designers on this list back here. And also, there's this constant competition with the quantum computers where a classical algorithm designer says, oh, I've figured out a new way to attack this problem. So we're advancing the research there, because if you find that new way, you can now start competing against the quantum computer. So that's the idea behind what we're doing. If you have problems that take you a couple weeks to solve right now on a supercomputer, I would love to hear from you. If you are someone that does these algorithms or wants to be working on these algorithms, I would love to hear from you. And with that, I will get back the floor.
Any question for?
Yeah.
Thank you so much. Maybe the questions are going on the panel after, or?
A quick question.
What was the question? I'm sorry.
Thank you so much. This is very valuable. I think I heard a little bit about the project yesterday, but this is awesome. I wanted to pick on the Ethereum smart contracts repository and how do you deal with the homomorphic nature of smart contracts in Ethereum, and how is the process of making it quantum resistant? And again, all these blockchains are, you're right, going through the same thing, but this is
like
awesome.
An audience plan. I love that. Yeah, so obviously we're building the gun against elliptic curve cryptography, for lack of a better term, right? Because we're accelerating the progress. And certainly we're going to be looking at that problem, because one of the main problems, and this has been known about since the late 80s, early 90s with Peter Shor's algorithm, you can look that up, SHORS, is that quantum computers happen to be particularly good at breaking the discrete log problem. That's the problem where, I don't want to get too much in the math. I'll leave it at the smooth brain level.
We're at MIT, you can go hard. Let's good.
So discrete log problem, look it up if you want to learn more. And, so one of the things we had to do as a prerequisite for building out this network, where we're trying to take advantage of these quantum computers, is build in signature algorithms that are post-quantum secure, and the cryptography is post-quantum secure, right? So we have that published. You can go to vault.quip.network. You can sign up for it on any EVM network, and the problem is pretty much solved. I mean, there's more to it, but the other aspects of the problem are much faster to solve. And the short answer is that we've had post-quantum cryptography for about 7-8 years now that I think is pretty good. It became an issue maybe 2010 era, when we realized, oh, these quantum computers might be 30 years away, so we have a store now, decrypt later problem with cryptography. We need to have solutions now. And then NIST started working on it, and then they released that stuff. So I think all that stuff is pretty reasonable to assume is trustworthy. And our personal solution is using a solution that goes back to the 80s, hashes. So we're using a hash-based signature algorithm that protects you, and you're happy to go online and learn more. Also, if you put funds in that, I'm going to do a little bit more self-promo than I expected. You'd be eligible for the airdrop for Quip Network too. So definitely check it out, vault.quip.network. So thank you.
Thank you,
congratulations. I love the problem.
That's awesome, thank you.
Yeah, great question.
Thank you.
Yeah.
Are you like a decentralized group that are you like a marketplace?
That's exactly what we're trying to do. We're trying to take the quantum computer manufacturers and other high-performance computers. We're specifically targeting problems that are very good for quantum computers to solve. All right, so right now, that's largely the annealing problem, so what D-Wave does. But it will become a more generalized system.
Because some labs are free, right, for now?
You can get 10 minutes on IBM for free. You can sign up for the D-Wave Quantum Leap program. They'll give you an hour a month if you qualify. But in general, it's about $100K to start, to just get and then they do like a 1 or 2 month consulting period to see if the problem even applies to you. And then if they think that the quantum computer will help you, then they'll give you access to it. So it's like a huge barrier to entry right now. Whereas what we're going to do is boil the problem down into give us a CSV and we give you the answer 5 nanoseconds later. Yeah, so it's a very different world. So, but the consequence is you're not building your own algorithms. You have to, know that your problem can be made to fit into that, and then know that it might help you or not. But you can test it really cheaply for like 50 cents. That'd be great, right? All right, thanks so much.
Yeah. Yeah. Thank you.